Let's focus on the Castells algorithm. This is very similar to the actually approach we discussed in the previous week. And here we make use of actually some drawing. With the help of drawing, we can obtain the Bezier segments. And if you remember the previous approach, we said that if you have a quadratic curve, what you need to do, you need to have some specific alpha and beta values, and then place your, let's say, points. I want to draw it now here. Yes, assume that we have 3 control points and we want to draw a quadratic curve. What we do, we set an alpha value. Assume that this is again something 0.2, and we mark it again on the second curve, and then we have another line. This is a 0.2 of it, the first point. And right now I'm also solving the quiz question. This is for alpha 0.2. And then I draw another one. This time alpha is equal to 0.5. And here alpha is 0.5. I connect these two. And again, find alpha equal to 0.5. Okay, this is my second intermediate point of the quadratic curve. The first one, the second one, and also we will have the start point and the end point. Now I will have another alpha value. Let's assume that this is alpha equals to 0.8, and I want to find it also here on the other linear portion. So I will join them together. And now I will mark alpha once again here. It should be around, right? So that will be my third intermediate point. So now what I'm going to do, I will simply join these points together. Let's use blue. So this is the first, second, third, fourth, and the fifth points. So that is what I was asking in the quiz. So this is our quadratic curve, quadratic Bezier segment. Any questions, guys, on this quiz question? And now we will make use of these fundamentals for higher order Bezier segments. Any questions? Now I will show you a website. This is here. You can also have a look at it. It should be already open. So now let me share it with you. Yes, they have a nice applet here. Now they have 4 control points. So the resulting Bezier segment is a third order. And you can see that they're following the same approach. Let me annotate it. For instance, at this point, let me see if yes, it's drawing. This is the first segment, right? First part, first linear part, second linear part, third one. And for the let's say cubic splines, we first need to find the quadratic, 2 quadratic segments, and then join them to obtain the cubic segment. So what we do, this is again for, as you see, this is alpha. Alpha is equal to 0.45, the first point on this curve, the other one here, and then we join it together. And again, this part is equal to 0.45, and the other part is equal to 0.55, right? So this is, if it was a quadratic curve, we would repeat this process for, let's say, some number of times and then join them together to obtain the quadratic curve. But here, our aim is to find a cubic spline. So what we do the same. We try to find the point for the quadratic curve, which is obtained with the help of the last 2 linear segments. This time, we'll consider the one between green and blue, and also blue and yellow. So I need to also consider this part. Now we join it together. This is another point on the quadratic curve. So this is second order. This one is also second order. But if you join these two, let's say, points together and again find the defined alpha value on that line, that will be a point on the cubic spline. That's it here. So if you repeat this process for n number of alpha values, then you can simply join it together to obtain the cubic spline. Now we can see that if I increase it, oops, me stop annotating. You can see how this, since it's a cubic one, so this point at the center is important for us, is drawing the cubic spline. Oh, you can see when this alpha is equal to 1, it should end at the yellow end point. Another thing, if you follow, for instance, this point, that will actually draw a quadratic curve between these three control points, red, green, and blue. And the one here will draw you a quadratic curve between the control points, green, blue, and yellow. But since we are looking for a cubic spline, that's why we should join this to second order curves to obtain the third order. Any questions on this issue, on this algorithm? A nice one. No questions? This website is a nice one. If you are interested, there are also other tools for Bezier splines. You can play with all the parameters, all the ratios. And there are also some easy code to implement. If you are into it, you can have a look at and play with these parameters. It's another thing, for instance, a similar approach that again using the Castellano. So let's go back to the slides. If you have any questions, I can spend some time on this one, but I think it's all clear. And now we will actually discuss spline curves, and it's about chaining the spline segments. In the previous ones, we just focused on some Bezier segments, or let's say Hermite segments. These were like curves in between two endpoints. But right now, we will try to find a way to join actually many of these segments together. And we simply call them as spline curves. May have single polynomial, and the previous functions may be actually utilized for the other segments as well. If you are joining, let's say, Bezier curves after each other, you need to use the same basis functions. So if your parameter is in between 0 and 1, then that means that value is defining the first segment actually. But if your t is between 1 and 2, then you will be referring to the second segment in your spline curve. So if you have the definition, if you have the formulation of your spline curve, then by changing this t value, we can focus on specific segments. And this is summarized here. We have the overall representation of the spline curve, and it's defined, as you see, with discrete kind of functions. And these functions are a bit different for each interval, since their coefficients might be different. But the thing is that if you join segments after each other, then you might have some discontinuities. For instance, think about the simplest case, a piecewise linear case. These are all separate segments, but we don't have any continuity. These are discontinuous, so we have just C0 continuity. So I can draw it without removing my hand. It's a kind of continuous curve, but its continuity is C0. But if you match the derivatives, then that will be C1. So if you have such, let me have a kind of a thing. For instance, assume that this is the first part and the below one is the second one. Then the thing is that at these connection points, if you have the same derivatives, then that's an C1 curve. This is C1. So in the piecewise linear case or other ones, we are simply multiplying the functions with kind of coefficients. But in the piecewise case, it's much simpler. We are multiplying the function with the points. That's actually an example. And another example, but this time we are dividing the curve into coordinate functions, y and x functions, as you see. And this is our piecewise linear case. And if you divide it into y and x coordinates, that will be the result. And depending on the t value, as you see, t is 0 at this point, at the first control point, then that will be equal to 1 at the second control point. It's not that complicated. So the basis functions, these we can assume that these are actually the basis functions of the segments. So if this is the first segment, let's say, then this is the basis function for the first part, and the other one is also here in x and y coordinates. And they simply actually reveal the change of these functions according to the change in the control points. So this is a very important issue. The basis functions actually control the resulting spline. So if you remember, these were the basis functions for the Hermite curves, and this is for the Bezier curves. And now I will show you that if you look at the Hermite basis functions, they're kind of continuous, right? This is the first, assume that, or I can say that this is the intermediate part. And you can clearly see that these all functions are continuous. There's a nice property of Hermite basis functions, and it's just due to the actual tangent property. Since if you remember, we were using the start points, start endpoint, and starting tangent and ending tangent as the control points. This is starting tangent, ending tangent, and this is first part, first segment. And obviously this part is the second segment. And you can see that the end tangent of pi is equal to the starting tangent of the second segment. And this actually helps us obtain kind of continuous basis functions. You see that it's also the same for the third part. This is the third segment. And again, the end tangent of the second segment is equal to the starting tangent of the third segment. And it results here, as you see, we have continuity. The derivatives are continuous. So we don't need to worry about at least C1 continuity. So this is C1 continuous. Any questions, guys, about the Hermite curves? But on the other hand, for the Bezier ones, we don't have actually built-in continuity in the basis functions. In Hermite, we have such continuous functions, but in Bezier, that's not valid. So we don't have inbuilt, let's say, C1 continuity. But how we obtain C1 continuity? We try to have collinear control points. This is a bit tricky. This is, let me mark them. This is the blue part. And let me use other colors. Oops. and it's also the control point for the second part. Let's make it larger. So what we do here is that we try to obtain, try to actually adjust the control points so that they will be collinear. So if you look at here, this is for instance P-1, P-1, P0, and P1 are all on the same curve, as you see, same line. So they are, we can say that they are all collinear, P-1, P0, and P1. And with the help of this property, we can obtain C1 continuity. Otherwise, it's not possible. Since we are not dealing with the tangents, starting or ending tangents, it's not available in Bezier curves. So that's why we have such a tricky way and try to obtain C1 continuity with the help of putting all these control points on the same line. And if you look at here, it's also the same. Since that this is P4 this time, these three control points are on the same line. Now, with the help of it, we can have such a continuous C1 continuity, having C1 continuity, let's say spline. So this part is segment, but the whole curve we can name it as a spline. So any questions, guys, about the Bezier basis functions or Hermite Bezier functions, how we obtain the continuities? So how we do the control actually? What is the advantage of having control points? How we can play with them? And the most important thing about these splines is that the control points will only affect the segments which it belongs to actually. It's not affecting the other regions. If you look at this example here, we are dealing with actually playing with this control point, and it belongs to this part, this segment. So if you move it, then only this part will be affected. The other parts, the other regions of the whole spline will not be affected. So that's why we say that with the help of this spline approach, you have local control. This is sometimes, depending on your again application, it might be advantages or disadvantages, but we usually use it for our purposes. So if you do not have it, then it will be quite difficult to use the splines. But in the, for instance, the natural splines or polynomial fields, you don't have, since that this is kind of data you obtained. Once you have a kind of a polynomial fit, and if you change data later, then you will have a total different curve, and the new curve will be modified a lot, but this is not the case in the splines. You can only modify a kind of a local region. Another property in the control is the convex hull property. Let's first define the convex hull. What is a convex hull? Assume that you have such points, okay, on the plane. And if the convex hull of this region is actually asked, then how we obtain it? We kind of actually put a rubber around these points or pins. You can consider them as pins. We are trying to put a rubber around and try to obtain this convex hull of the point. So let me do it. So that is the convex hull of the given set of points, which means that the resulting polygon is a convex one, and all the points are inside this convex region. So what is it, why it is important for let's say splines? Since some types of splines actually stay inside this convex hull of the control points. This actually helps us a lot. The things like clipping, culling, picking, or other operations are highly simpler. You don't need to use complicated algorithms since they're always in the convex hull. For instance, these are control points, and the resulting curve is always inside the convex hull. But what about the last one? Obviously, this is not inside the convex hull, and it's sometimes you may come up with such cases, but this time then such operations will be quite difficult. And how you obtain it? You can obtain it by using positive basis functions. But if any of the basis functions has negative values, then you cannot have this convex hull property, and you need to spend more time, do more computation for the clipping, culling, or transformation operations. So how we are going to actually chain all these segments? And the Hermite ones are not that difficult, since we make use of the tangents. If the end tangent of the first part, let's say, is equal to the starting tangent of the second part, then you can easily join them together. But on the Bezier side, it's a bit different. The advantage of the Bezier curves is that you just have the points. You don't play with the tangents. But the thing is that you cannot have C1 continuity by following irregular points. You can only have it by using the collinear points. And another thing, another weird thing about the Bezier curves is that it's interpolating every third point, which is quite actually weird. Let's show it here. See now, this is the first curve, first Bezier part, and this is the second Bezier segment. And as you see, it's interpolating every third point, but it's approximating these interior regions. It's not going through them. On the other hand, Hermite curves actually are always doing a kind of interpolation. They're always going through the control points, which is sometimes a nice property. So you should be aware of this property of Bezier curves. They always interpolate every third point. But if you do little modifications, if you make it C1 continuous and C2 continuous, you may have other, let's say, points also included in the interpolation. But now we will try to find a different, let's say, type of curve. This is called as Cadman-Rom splines, and we will follow a similar approach like in the case of Hermite splines. But this time we will continue from the Bezier curves, use the approach we utilized in Hermite curves, and obtain a new type of curves. And this is called as Cadman-Rom splines. So what we do this time, we don't have any right now interpolating splines. And if you have kind of tangents which are valid for all control points, then things will be quite easy. So in summary, if you have tangent vectors for all control points, then you can easily define a kind of an interpolating spline, interpolating curve segment. So what we do for that purpose, we make use of the adjacent control points. So for this one, how do we obtain the tangent vector? We make use of the adjacents. This is the left adjacent, right adjacent point, control point. So we have a line connecting this one, these two. And then now we will draw a tangent vector here, which is parallel to the line which is joining the adjacent points. And we do the same for the other one. Yes, now we have tangent vectors for the intermediate control points. And with the help of it, we can obtain a kind of an interpolating spline. And this is called as Cadman-Rom splines. Now have a look at the math behind this approach. And now we will make use of the property. We obtain the tangents as a kind of a subtraction between the adjacent points, and we scale it by half. So this is our control points, and we have two extra, let's say, control points, but this time not points, control things, let's say. They are, again, tangents in the case of Hermite, but these tangents are defined at the intermediate points, not at the start and the end points. And this is how we do the definition of these tangents. This is a subtraction between the control points, adjacent control points, scaled by half, and this is also the same for the second intermediate point. So this was the matrix for the Hermite splines, Hermite curves. Now this we are kind of doing a modification, transformation between the Hermite curves and the Catmull-Rom curves. So this is what we do here. We do a kind of multiplication and obtain the matrix for the Catmull-Rom basis functions. So you see here an example. We have 4 control points, and for the intermediate ones, we define tangents, and these tangents are defined with the help of the line actually going through the adjacent points. For instance, if you consider the P1 control point, this is an intermediate control point. Its adjacents are P0 and P2, so we draw a line in between and have a tangent in that direction. And it's also the same for the second intermediate point. So its adjacents are P1, P3. This is the line in between, and we draw a tangent parallel to this line right on the control point P2. So this way we can obtain 2 extra controls, and these are tangents at the intermediate points. And resulting basis functions are like this one. They are quite symmetric, and we can obtain an interpolating spline with the help of this approach. As you see, there is no approximation. And again, we have C1 continuity. They are all continuous. They have continuous derivatives. So this is a first example of an interpolating spline. Like Bezier, again, is equivalent to Hermite. We have done such little modifications. They are, in summary, actually, all these type of curves are similar to each other. We can say that they are equivalent, just their coefficients, their basis functions are different. And right now, we will have just a first example, which is based on a control point sequence. And another thing about the Catmull-Rom splines is that they do not have convex hull properties. So the operations like clipping, moving, other operations are quite difficult, but it has an interpolating property. Any questions, guys, up to now? Now we will jump to a different topic. And these are called as B-Splines. Actually, B stands for basis splines. But this time our aim will be to obtain splines having continuity higher than C1. Another issue, depending on your application, you may not need an interpolating spline. This is actually only possible with the help of these B-splines. They're highly flexible, and you can obtain very long splines. And another thing is that you can have arbitrary order of continuity. So this is up to you, up to the coefficients, type of basis functions you are using. So it's a very flexible way, and we will now have a look at how we obtain this kind of curves, splines. You'll see the construction. So we can do it by simple convolution, and or have some kind of sampling and reconstruction also at the same time, but not that difficult. I will show you an example now first. This is the cubic B-spline basis. And here you see we have 4 control points, but it's not going through any of these control points. It's a completely an approximating basis function. But it's up to you. You can modify the things and have it kind of interpolating at some points. It's up to you. We will discuss such curves in a moment. And below you can see the basis functions for this segment, for this cubic B-spline segment. And you can, if you use the same functions, same basis functions, you may have, as you see, such continuities again, C1 continuities, and you can easily add more control points to your, let's say, segment. But again, it's an approximation. This time, it's completely an approximating curve. So how we derive these splines are quite different than the other Hermite or Bezier curves. We need to have 4 control points, 4 active control points, and this time we will have C2 continuity. And once you have them, have these information, then you can easily derive the things, the coefficients, other things related to your splines. And we can do it for actually all orders, not just for cubic, quadratic, or 4th order. So this is the terms we're gonna use. Once you say order D, then that means its degree is 1 less than that. If you have an order D, then that means you have D number of points which are contributing to a specific value of the spline. And for that purpose, we will be using a kind of a mathematical, let's say, function or a recurrence. It's called as Cox-de-Boer, and this is the main equation, and they will be actually defining the basis function we can use for the B-splines. This is a starting point, and as you see, let's say if you want to obtain B2, then if you want to obtain B2, then you need to know B1, and here T over 1 times B1 of T plus, again, if D is 2, then we will have 2 minus T over 1 times B1 of T minus 1. So this is the second basis function. And if you want to obtain the third one, again, you need to use the previous basis function. So that's why we call it as a recurrence type of basis functions. We use the previous basis functions to obtain the next ones. And let me show you in a graphical way. Here you see the basis functions. They're all kind of actually ramp up and ramp down motions. So here you see it's going up and down, going up, down. So they're all ramp up and down kind of functions. And as we go further, you'll see here they become smoother and their maximum value decreases. So what we do, we make use of all these basis functions. We take the convolution of these and try to obtain the resulting spline. And if you want to make it smoother, then that means you should obtain higher orders. And this is done with the help of increasing the orders. And this is the, let's say, mathematical definition for a cubic spline, cubic B-spline. These are all our control points, and this is the basis functions. You can obtain them. And this is the parametric part. This is our parameter set, and we have 1/6 here, is quite important. So now, instead of just using the parameter space, we can make it like written here, starting from T min to going to T maximum. So instead of having smaller segments, we will have the whole range under control, and that will be much simpler. And if you want to join segments to each other, then you need to make use of knot points. So let's have a look at here. These are our control points. The diamond ones are control points. And this is the resulting B-spline. And if you look at here, we have some connection points. These are nuts. And nuts are obviously in between the curve segments, and they all have a kind of a nut value. And for n+1 points, we should have n-1 nuts. So this is a kind of a rule. Once you follow the approach, you will obtain this number of nuts for n+1 number of points. So if you look at our example, we have 10 control points this time. M is equal to 9, and that means we have 8 nut points and just 7 segments. And these segments are all, I think, should be cubic since they are valid for 4 control points. Any questions, guys, about these B-splines or other types of curves, their relations between each other?
Hocam benim teacher, I have a question. Is there any specific rule or something why we started with T3, or numbers are just something to show?
We start with P3. You asked why we start with third order.
Yeah, normally in the equations we start from T1, T2, T3, but we directly started T3 in here in this example.
It has an intermediate complexity. If you just focus on the second order, that will be too simple. And if you increase it to, let's say, 4 or 5, then things will be getting larger. The size of the matrices will be larger, but the fundamentals are the same. So, and another thing is that the cubic splines are the most frequently used type of splines, and they are computationally good, since if you increase the order, then you need to spend more time for the computation. Another issue, cubic splines are usually represent any kind of curves. For most of the time, for about, let's say, 90% of the time, they will be enough for your application. That's why we usually focus on the cubic splines. Now we will focus on a bit different type of B-splines. This time they are non-uniform. In the previous one, they are evenly the same. For the, let's say, cubic region, this part and the other part, we use the same basis functions. The basis functions of all these segments are the same. Their just control points are modified, but the rest is the same. But now, in a non-uniform case, we don't have an even space of, let's say, segments. The discontinuous are not even space. We have uneven distribution, and this time, with the help of it, this uneven distribution, we can have full control. We can have sometimes interpolation at certain points, or sometimes approximation. And again, if you look at the previous one, this is fully an approximating B-spline. But now, with the help of non-uniform B-splines, we may have at some points interpolation or approximation. It's up to our kind of definitions. We will see the details in a moment. Another thing, we mostly prefer to have interpolation at the endpoints. So usually we want actually our spline start at the defined point. Let me switch to here. For instance, you may want your spline start directly at this starting point, or you may want it end at this directly end point. But in the simple splines, B-splines, which are evenly distributed splines, you cannot have this property, since they are all approximating. But in the unevenly distributed case or non-uniform B-splines, we can have such a control. And these type of curves are called as non-uniform, rational, since we will see that we will have some rational functions like this one, for instance. They will help us a lot. With the help of these rationality, we can even define complicated points, complicated curves. Even the cones can be represented with the help of these NURBS. So this is called as non-uniform rational basis splines, and we prefer to use this abbreviation as NURBS. And probably you have heard about it. It's a very popular type of representation, type of spline, and many of these of the CAD software these days are actually using NURBS. For instance, rhinoceros depend highly on NURBS, curves, and surfaces. So what is the advantage of this type of NURBS curves is that they are invariant. So even though you change the space, even though you do translation or kind of things, they will not be modified. They are always the same. So this is another advantage of it. And lastly, you can represent any kind of surface, any kind of curve with the help of this non-uniform rational basis splines. So the thing in the B-splines or NURBS curves is that we need to have a kind of a knot sequence. So this is a highly important issue, maybe the most complicated thing in the NURBS curves. If you cannot define the knot sequences properly, then you will fail. So in the B-splines, we have even distribution of knots. In the uniform B-splines, and we know that curve is not interpolating, it's always approximating. But once you have the uneven distribution of the knots, then that means you are working with the non-uniform B-splines. You are working with NURBS. So in the uniform case, if that's the kind of a curve, you always have kind of knot points, and they're always uniformly distributed, and you have just one of these in the sequence. Let's say if this is a knot sequence, and if these are knot numbers, you'll just have such kind of values. But in the NURBS case, we will see that in the knot sequence, we will have we will sometimes have repetitions. For instance, if it's a third order, we may have 3 zeros and then 1, 2, let's say, and at the end you may have, if you want to have an interpolation through the endpoint, you need to have the same value as the order. Okay, if it's a cubic, you need to have 3 of them, and at the end, if you want to have an, let's say, if this is the endpoint, if that's the starting point, you need to have 3. If it's a cubic type of spline, you need to have 3 0 actually not, and 3 n not at the end of this sequence. I will show you some examples in a moment, but this gives us a high flexibility. With the help of it, we may sometimes have interpolating. Your spline may be going through that control point, or depending on your knot sequence, it may be just doing a kind of an approximation. So we do it, actually we are kind of tying it at the starting points for 3 times. So this is, since this is a knot, so we are kind of tying this curve 3 times at the starting point and then let it go. And that's why it should pass through the starting point. And it may not be this actually case. For instance, let me have such control points. Again, I will draw a kind of a cubic spline. For instance, that might be the cubic spline. But here, as you see, it's not going through the start or the end point, but it's going through an intermediate point. If that's the case, then that means we are tying it 3 times at this intermediate point. And then what I'm going to write as a knot sequence is that this is a 0, 0, 1, 2, 2, 2, and then 3 and 4. If that is your knot sequence, then I know that your spline is going to interpolate the third control point, but it will approximate the rest of the control points. So this is an, as I said, very flexible way And let's, if you have one more one here, in the new case, let's say you have 1, 0, 1, 1, 2, 2, 2, 3, and 4, then probably your curve will go closer to this one and then do an interpolation through the third one. But if you have 3 ones here, then for sure I know that your spline will exactly go through this control point. So in this a cubic spline, if you have 3 repetition for that knot, you will be tying it very firmly at this control point 3 times, which means that your spline cannot go elsewhere. It should directly go through that control point. Yeah, this is actually what I mentioned. If the knot value is repeated, then the effect of that control point or that blending function will be increased. The weight of that control point will be highly increased. And that will result in an interpolation, not an approximation. So if you have just a single knot value, then that will be an approximation. But if you have repetitions, then you will be approaching to interpolation. So as I'm showing you, if you repeat d times, then it will, your blending function will converge to 1 and it will be an interpolating control point. Any questions, guys, about this issue, a very important issue about B-splines and nerves? Okay, we can see the example here. We have the degree of the curve. You can see right now we have second order, third, again third order, fifth, and ninth order. Now let's have a look at these knot sequences. And I see that we have repetition right here. And since it's a second order curve, the degree of the curve is 2. We should, if you have 2, let's say repetition of a knot value, then that means we should be interpolating. And it's the case, as you see here, our curve exactly starts at the starting point. But if you look at the rest, it's not going through any control points. These boxes are the control points. And these dots are kind of knots, let's say, knots of the spline. And they're not matching other than the starting point, right? And if you look at the knot sequence, as this is the thing actually we are expecting, we don't have any other repetition. We have 1, 0, 1, 2, 3, 4. Let's write 4 here. 5, 6, 7, 8, and 9. So we have 9 control points. This is 0, 3, 2, 1. And we only have a repetition at the starting point. And that's why we are interpolating the starting point, but the rest is just approximated. Now let's have a look at the second example here. Again, this is our knot sequence, and we have 3 zeros here. And other than that, we don't have any repetition, right? So we are expecting that our resulting spline should be going through the starting point, but it shouldn't go through any other control points. And if you carefully look at it, that's true. It's only doing an approximation except the starting point. But now let's focus on the third example. Again, the degree of the curve is 3, but this time we have a different, let's say, knot sequence. The control points are the same, just we modified the knot sequence. So we have a group here, another group here, another one, another one, another one. So this is the starting point. Obviously, we have 3 of them, so I know that it should go through the starting point, but then I have 2 repetitions of 1. But this time, since we are repeating to 1, we have decreased actually number of control points, number of the NOT points, it has a maximum value. You cannot have, let's say, 3 times 9, 27 values in this sequence. It's not possible. In maximum, you can have, let's say, we have 9. I may have 2 extra, so we will have 14 NOT values in maximum for this curve. So this is actually what we have done here, what is done here. So we have 2 repetitions of 1 here, then that means it should be kind of touching one of the lines, but it will not again do a kind of an interpolation, since we don't have 3 of these ones. If it was 3, then we should be going through this point. And it's also the same for the other intermediate points. And now you see that this time we have 1, 2, 3, and 4 segments. In the previous one, since this was second order, we have many segments. But let's have a look at here. This is the first segment, 2, 3, 4, 5, 6, 7 segments we have. But now we have 4 segments. And that's why, in other words, we say that this number cannot go beyond this 4. And if you look at the last point, last region, again, we have 3 or 4s here. So that's why we have an interpolation. And now let's focus on the fourth case. For example, this is the degree of the curve is 5. So if you have 5 repetitions of 0, then that will be an interpolation at the starting point. And then we have 4 repetitions of 3 and 5 repetitions of the last point, 5. So again, it will be an interpolating, but since this one just have 4 of 3, we cannot have an interpolation, but it will be an approximation. It's very close to this value, but not going through exactly that control point, since we don't have an extra 3 here. And lastly, this is the degree of the curve is right now 9. And if you look at the NOT sequence, we have 9 zeros and 9 5s. So which means that our spline should interpolate between the start and the end point, but it should approximate through the other control points. So now you can say that these knots are actually distributed parametrically, and with the help of T, you can move your point anywhere on the spline. We have 10 control points, obviously, and you can have as many segments as you have actually non-zero intervals in the T. So this is how we use the knots, and the knot selection is highly important in determining the profiles of, let's say, splines and nerves, B-splines and nerves. So how we do the conversion between the splines, different type of curves, or it's not that difficult actually. If you remember, while we were discussing Hermite, Bezier, Cadmus splines, they all have some kind of matrices defining the coefficients and also the basis functions. And in this example, any spline can be represented with any type of curves, provided that you have the proper matrices. And we have the parameters here inside T of T. By doing proper, let's say, conversion between the matrices, you can easily convert one type of curve, let's say Bezier curve, into Hermite, or Hermite to a Cadmus splines, by having different control points. It's not that difficult. With simple multiplications, matrix multiplications, we can do the conversions. So let's have a look at here. Compare the type of actually cubic splines. And we have the local control in all of them. We have continuity in Hermite, Bezier, Cadmus splines as C1, but we can have C2 continuity in these splines. And if you look at the interpolation case, as we may have in the first 3, depending on your let's say distribution of the control points, it's a bit different on the Bezier. That was the kind of question in the quiz. But in B-splines, if it's not a NURBS curve, the pure B-splines actually do not have the interpolation property. They are always approximating. So there's a question about the quiz. Talha, did you submit it?
Yes.
So can anyone tell me the answer to the quiz?
Teacher, is it both of them, both of their tangents should be equal in that point?
Yeah, we need to have C1 continuity, or you may have them on a collinear line, as Brock has written on the chat. If you put the same points, put the previous and the after point on the same, let's say, line, then you will automatically satisfy the derivative equality and you will have C1 continuity. So that was not that difficult. Any questions, guys, regarding the quiz? Okay. So now let's go into a little bit details of NURBS curves. We said that it's the abbreviation of non-uniform rational basis splines. And these days, most of the CAD software uses such type of curves. And we can have different shapes, different, let's say, lines represented with them. Even surfaces can be represented. And there are different algorithms for evaluating such curves and surfaces. And the advantage is that they are invariant under any kind of transformation. This is the main advantage of NURBS types of curves and surfaces. So what do we mean by rational spline curves? Then that means we have a kind of ratio of two functions, and this resulting spline curve will be invariant under these operations, under rotation, scaling, translation. The profile of the curve will not be modified. So the simple thing is that you will be transferring these control points. If it's a kind of a translation, then what you do the generation at these new points. You don't need to completely transfer the whole curve. You can easily regenerate them at the new control points. The thing about the non-rational ones, they're only invariant under rotation, scale, and translation, but the rational splines are quite have much invariancy compared to non-rational ones. And with the help of them, we can define the conic sections or another kind of analytic functions easily. And for the conic ones, we require some quadratic polynomials. But it can only be approximated with non-rationals. They cannot exactly represent with non-rational ones. So what is our basic idea? We will have four-dimensional non-uniform B-splines, and they will be normalized with some homogeneous coordinates. So if you think about pi, let's say, if pi is represented with x, y, z, and 1, then the results will be invariant with respect to any kind of projection. If you remember our Cox-Tabor recurrence, you may have not spacing arbitrary, depending on your, let's say, requirement, whether you want to have interpolation or approximation. Obviously, we know that if the knots are close together, then the influence of some of the control points will be improved, and the duplicates one will cause some of the points to interpolate. For instance, in the NURBS curve, if you have such an knot sequence, the result will be simply a Bezier curve, a cubic Bezier curve. Since in the Bezier, if you remember, our curve was interpolating for the start and the end points, but it wasn't interpolating through the intermediate points. So it was an approximation at the center and interpolation at the ends. So that's why if you have such a knot sequence, you can obtain a Bezier curve. And lastly, what about rational functions? These are such rationals of separate functions in terms of the same parameter t. we have a common value in the denominator. This is W of t, and they are all cubic polynomials if you are defining a cubic nerve segment. And they are all homogeneous coordinates. And for the 2D cases, if you are working on the plane, then you're not going to have z of t. You will only have x, y, and w. So let's have a look at an unit circle on a plane, on an xy plane. We said that we shouldn't have z of t, but if you have these coordinate functions defined like this, then you will obtain a unit circle on the plane. And this is again represented with the help of rational functions. There's another circle in 3D homogeneous coordinates. And I think this is the last topic of this chapter, the offset curves. What's an offset curve? If you have, assume that this is the original curve, and if you want to draw an offset to it, you may have inner offsets. This is the inner offset. This is obviously inner one, and you may have an outer offset. So depending on the parameters, you may increase the size of it. This is outer offset. Again, you can do it in a parametric wave. And this is actually obtaining tangent. Once you obtain a tangent, then you can determine the normal. This is the original curve. If you define normal, let's say, and then move on that normal a little bit, assume a distance like d, then that means you will obtain a value on this inner offset. And once you obtain the normal curve, things are much easier. But if you have a very complicated curves, it will take lots of time. The computational cost is a bit much. So you need to be careful about the definition of these parametric curves. So we can simply define the offset curves as, or even the parallel curves like OD of t. These are offset curves or parallel curves. How we define it? We have the original curve definition, and then have an offset value or a parallel value. This might be any value in a number, and we move our curve on this normal vector by an amount d. And if d is negative, then that means that will be an internal curve, internal offset with some positive value, which is positive in the direction of normal curve. Then it will be an outer offset. You can see an example, for instance, spade. The red one is the original curve. You see the inner and outer offsets. So if you look at here again, normal. If that's normal, then if you have d value in the opposite direction, then you will obtain an internal offset. And if you increase this d value, you may have smaller curves, as you see. As d goes higher, at some point you'll just have a single point, or once it's a very high value, then you may not be even able to define the internal offset.